seminar. Okay, so we are very excited to announce the series of the Informal Number Theory seminar. So this series is meant to bring advanced ideas in modern number theory into accessible and conversational like the level for especially early like the stage of graduate like the students. So this seminar will be recorded basically for the majority of the talk. And if you guys have any like the questions and if you want to specify some of the like the detail in person, then please do not hesitate to raise your hand and we can just focus on that part and then we can just move on to the further like the conversation next time. So this seminar will be held in the bi-weekly basis and the topics would be chosen in random depending on the speaker, but we will see everything go eventually quite smoothly. So the first talk will be given by Chiloyan. So he's my very close friend. So he will talk about the Galois representation and isogeny-torsion groups. Yeah, thank you very much.
Thank you for the introduction, and thank you for the organizers for inviting me to give this talk. And thank you to everybody for coming to listen to my talk and those who will watch later. This is going to be a very terse talk about elliptic curves and how you can use Galois representations to study properties of elliptic curves, in particular, its algebraic properties, its properties on Galois representations. Okay, so if anybody's having trouble hearing me, please let me know. And if not, let's get started with the talk. Okay, so what did I say was what we were going to talk about? We were going to talk about elliptic curves. In particular, we're going to talk about rational elliptic curves. So a rational elliptic curve is a smooth projective curve over Q. This boldface Q is supposed to remind you of quotients. So quotients, in other words, the rational numbers. A rational elliptic curve is a smooth projective curve over the rationals that can be described by a Weierstrass equation that you see over here in three different variables, x, y, and z, where a and b are rational constants. And where smooth comes from, smooth means this 4a cubed plus 27b squared term cannot equal 0. So that's what it means to be smooth. So points on E are going to be of this form in closed brackets a, b, and c. A, b, and c are going to be elements of the algebraic closure for the rationals. But one thing I want you to note is that not all of them can equal 0. This square bracket is important to mention that points A1, B1, and C1 and A2, B2, and C2 on E will be equal if and only if there's a scaling term between it. So if there's like a lambda that multiplies A1, B1, C1 to A2, B2, and C2, then actually those 2 points that you started with are equal. That's what it means to be a projective curve. There's a single point at infinity on an elliptic curve. I mean, a point at infinity when z equals 0. So if you look at this equation for E, if you plug in z to be 0, you could see that x cubed must be 0. And because we're working over algebraic closures, meaning fields, then x has to be 0. So if x and z are 0, then y is not 0. We can just say this term is the point at infinity O is 0, 1, 0. Well, it's nice to work with the homogeneous form like we see here, but it's also good to dehomogenize, meaning you rewrite it in a way where you can eliminate this z term and we get this term. Y squared equals x cubed plus ax plus b. But I lost the z term. How do I kind of reconcile it? Just keep in mind that the only time that you have to worry is when z equals 0. Everything else kind of gets absorbed into a, b, and c. But when z equals 0, you have this only singular term, o. So just keep in mind this term, o. And if you're okay with that, you can just view the Weierstrass equation in terms of two variables, x and y. All right, so elliptic curves are of this form, y squared equals x cubed plus ax plus b, with an additional term, 4a cubed plus 27b squared. That term cannot equal 0. All right. Well, that's a
Before we
nice,
proceed, we have a nice question from the chat.
yeah,
It
let's
says,
go ahead.
since you're defining the curve over Q, isn't it true that ABC should be in Q rather than Q bar? Could you explain why we are taking Q bar instead of Q?
If you can hold on your question for another 10 minutes, that would be extremely clear. But I don't have a good way to describe this. There could be more, I guess, freedom if you allow algebraic closure of Q. For example, why not make y to equal I, the number that squares to -1? And then you have something like -1 equals x cubed plus ax plus b. That would be an interesting point. So why restrict ourselves to only rational numbers x, y, and z? So there's many more points that spring up if we give ourselves coordinates from q bar instead of q. So essentially, you can make any kind of coordinate system, but you want to make it so that the elliptic curve actually has nice structure, and the structure is what we're going to talk about very soon. So this Q bar is not done for no reason. This Q bar is done because we want to make this structure into an abelian group. The reason why I think we work with coordinates over Q bar instead of just Q is that there's a nice structure of an abelian group if you work with the algebraic closure. So what is a group? It's a nice algebraic object where you can add things nicely, or if you want to multiply things nicely, or if you want to do any other things nicely, there's a nice structure to that. But we have been studying groups for maybe 300, 400 years very seriously, and we know a lot about them. And if we can rewrite terms into into abelian groups, then things become very nice. And that's why we view points on an elliptic curve over Q bar instead of just Q. That structure of an abelian group is very nice. Well, what is an abelian group? Well, it's a way to add things together. And this is an example of an elliptic curve that my advisor Alvaro drew on his board many years ago. And this picture has been passed around many years, and you can see it now here too. I'm going to tell you how to actually add these 2 points. And in essence, this is like one of the most important parts of an elliptic curve, that you can actually add points on an elliptic curve together to get another point. Let's say you have these two unequal points, P and Q, on an elliptic curve, and you want to be able to add them together in a nice way to get a third point. Well, the structure of an abelian group gives you that way to add them together. So let's say you want to add P and Q together. The way to add them together is you draw a secant line, this green line connecting P and Q. That secant line hits the graph at a third point here. Let's draw a vertical line through that point. That line, vertical line, hits the graph at another point, R. This R is what the sum of P and Q will be defined as. So any 2 points that are not equal to each other, you can do this process. Pick the 2 points, make a secant line through it. That secant line hits the graph at a third point, make the vertical line. That vertical line hits the graph at that point, P plus Q. What if the point you're adding is itself? So you want to add Q to itself. You do the same exact thing, but instead of drawing a secant line, which is impossible because you only have 1 point, you draw a tangent line. So you draw this tangent line on the graph at the point Q. So this tangent line hits the graph at Q at another point here. And then you draw another vertical line. So this point here connects with the vertical line on the graph, and then you hit this point down here. This is 2 times Q. So with this operation of how to add points together, we get an abelian group, a group that is commutative. So if I want to add P and Q together, it's the same as adding Q and P together. This operation is commutative. And this is a very important property of elliptic curves. Not just any algebraic curve, elliptic curves have this very, very special property. Okay, let's move on. So before the question was asked, what if the coordinates of a point are both rational? Yeah, that's very interesting. So a point P with coordinates A and B on an elliptic curve E defined over the rationals, I will call that point to be rational if the coordinates A and B are both rational. And so we denote the set of rational points on E by this notation E of Q. So where you have this curve E and you have this Q term nestled between parentheses, you should think about points on E that have rational coordinates. So remember how I said E was a group in the previous slide? Actually, the points on E defined over the rationals is also a group. So using the same operation. But more importantly, it was proved 100 years ago or so that this set E of Q that we call the Mordell-Weil group after Mordell and Weil is actually finally generated group. So if E is an elliptic curve defined the rationals, let E of Q tors meaning torsion, denote the subgroup of this group of elements of finite order. Then this is a finite abelian group. The torsion subgroup of an elliptic curve is a finite abelian group, and there's a non-negative integer r, where you have this isomorphism. The Mordell-Weil group is isomorphic to some number of copies of z, the integers, times the torsion subgroup of E. This R is a very interesting topic of study for arithmetic geometers. In particular, we'd love to know how big this R can be. Some people think it could be arbitrarily large. We just haven't found examples for it yet. There is an example of an elliptic curve of rank 28. So an elliptic curve where this R is equal to 28. Is that the biggest example? I don't know. It'd be very interesting to know if that is the biggest possible, if there's any limit to how big R can be, or if there's one of rank 29, 30, I don't know. That's an interesting computational question. So we don't know much about this R, though there's a lot of research done on it, but we know everything there is to know about the torsion subgroup. So about 50 years ago, Barry Mazur proved that for a rational elliptic curve, the torsion subgroup is isomorphic to one of 15 groups. It could be cyclic of the form Z mod MC for one of 11 different examples. It could be isomorphic to a cyclic group of order 1 through 10 or 12, but not 11. Or it could be isomorphic to a bicyclic group, Z mod 2 cross Z mod 2, or Z mod 2 cross Z mod 6, or Z mod 2 cross Z mod 4, or Z mod 2 cross Z mod 8. These four groups, Z mod 2 cross Z mod 2n Z, n could be any integer 1 through 4. So this is a very important object, and I want to study these objects of an elliptic curve. Rank is very nice. I just want to study torsion subgroups though. So rank is very difficult for me. Torsion subgroups is a little bit easier. We talked about elliptic curves as group objects. That's nice. So typically in math, once you have an object, you talk about the maps between them. So if E and E prime are elliptic curves, both defined over the rationals, an isogeny is what we call a map from E to E prime. So it's a morphism. So a morphism has a very nice definition. I would suggest you cite it from an algebraic geometry textbook so I don't make a mistake, which I have it written down. It's just a very nice map between two elliptic curves with one caveat that the point at infinity on the one curve should be mapped to the point of infinity on the other curve. And we'll say E is isogynous to E prime if there's a non-constant isogeny mapping E to E prime. So the constant isogeny is the isogeny that maps E, all points on E, to just the identity of E prime. There's nothing wrong with that map. That's a nice map. It's an isogeny. But we won't say two curves are isogynous if that is the only isogeny you have. For two curves to be isogynous, we want there to be a non-constant isogeny, an interesting map. So a couple properties of isogenies. We'll say an isogeny is rational if it is defined over the rational. So there will be like rational functions that define the isogeny. If those rational functions have constants that are rational, then we'll say the isogeny is rational. As some group theorists had suspected, I'm sure, isogenies are group homomorphisms, which is what's so important of mapping the identity of the curve to the identity of the target curve. The cardinality of the kernel of a non-constant isogeny is finite. So if you have the constant isogeny, of course, the kernel is the whole elliptic curve, and that's not finite. But when the isogeny is not constant, then the cardinality of the kernel is finite, and we call the cardinality of the kernel to be the degree of the isogeny. And if the kernel is, let's say, a group H, then I'll say phi is generated by the group H. So the kernel and the isogeny have a very intimate relation with each other. They're very well described by each other. H, the kernel, and phi, the isogeny, seem to be 100% completely described by each other. And an isogeny is said to be cyclic if it is generated by a finite cyclic group. And of course, and also it's called prime if it is generated by a group of prime order. So this last point, cyclic and prime, come up a lot in the isogenies I work with, which is why I made a mention of it. So let's talk about examples of some isogenies. So I guess these would be some of the most important examples of isogenies. So an elliptic curve E is isogenies to itself because, of course, you have the constant isogeny. Sorry, not the constant, the identity isogeny. That's very nice. But there's also isogenies called the multiplication by M map, where let's say M is a positive integer. So you can map an elliptic curve to itself by taking each point and adding it to itself M different times. That's an isogeny because it maps the identity to itself. And it is, in fact, a rational morphism. And if, let's say, you want to do negative M of P, it's the same thing as doing M of negative P. And of course, if you say M is the zero, then the zero map is a constant map. It maps everything to the identity. A little bit more interesting is, let's say E is this elliptic curve, y squared equals x cubed minus x. Let's say I is the isogeny that maps a point xy on E to itself to the point negative x, iy. And it maps the isogeny, the identity to itself. Well, the kernel of this map is not trivial. It is trivial, but it's not equal to the multiplication by one map, and it's not equal to the multiplication by negative one map. And thus, this map I is not equal to any multiplication by M map for any integer. So this is a new type of map. And in the case of an elliptic curve, you always have the multiplication by M maps, like I wrote in this example. But when you have an example of an elliptic curve that has a map to itself, which is not of the form of a multiplication by M map, we say that E has complex multiplication. So this is a concept that comes from algebraic geometry. In the case of elliptic curves, this is specified as elliptic curves that have a big group of isogenies, like automorphism groups. So it's not just that you have multiplication by M maps, you have other more interesting maps of this form, let's say I. So this is a very hot topic of study in the theory of elliptic curves.
So may I ask one question in the previous
Yeah,
with this example? So if you go back to the previous slide, so
let's do. No. Here, go.
yeah, so you said an isogeny is rational if it is defined over Q. So if I interpret this incorrectly, let me know. So I just thought, well, so we have a inhomogeneous, like the expression of the biostats equation, so that we have a pair that consists of just a rational, and this isogeny maps to the new pair, and each of
Yeah.
the components should be rational. That's what I interpret this very first line. But from the example you mentioned by complex multiplication, so from the nature itself, it cannot be rational. Am I wrong?
This is not a rational morphism.
Because it's not defined over rational for some component.
Yes, because I is not rational. It's not
Okay,
rational.
then yeah, I have no issue. Yeah,
It
thanks.
doesn't work. Yes, correct. Very nice. Okay. Where was I? Any other question? Okay. So this is an example of an isogeny that is not e to itself. It's e to another curve. So the point of this example is not just about isogenies. Remember Mazur's theorem that I said I like to work with this Mazur's theorem. I want to now extend this Mazur's theorem. So we talked about elliptic curves, we talked about Mazur's theorem on elliptic curves, we talked about isogenies. Can we link these three together? So naturally, let's say E and E prime are nice elliptic curves. Why not connect them with an isogeny? Okay, that's nice. Well, now we have like a way to describe them in like a relationship. Okay, so would the properties of one elliptic curve affect the other elliptic curve if there's a relationship between them? Naturally, the answer should be yes, and it is indeed yes. So what I'm trying to say is, let's say E and E prime are elliptic curves connected by this isogeny T. Can we talk about the torsion subgroup of one in terms of the other? In other words, does the torsion subgroup of one make a determination on the torsion subgroup of the other? So, for example, E and E prime are these two elliptic curves. They are isogynous to each other. And I wrote the components of the isogeny here. E has torsion subgroup Z mod 4Z, cyclic of order 4, and E prime also has a torsion subgroup of order 4. It's not cyclic, Z mod 2 cross Z mod 2. So now my question is, can you classify all such combinations? So if you have two elliptic curves that are connected by an isogeny, can you tell me what the torsion subgroups have to be? So this is a difficult question to think about just by giving yourself pairs of elliptic curves. There are infinitely many elliptic curves. I don't know how you can kind of give yourself a organization of your thoughts just by isogeny, elliptic curve, and torsion subgroup. Well, how about we kind of give ourselves a visualization before we investigate this question further? So let's say E is an elliptic curve. Maybe I should have said define all the rationals. I'll say the Q isogeny class of E is the set of all elliptic curves over the rationals that are isogynous to E by an isogeny that is rational and has finite kernel.
Yeah, sorry, I have one question. So
Yeah,
please just point out my just ignorance. I just want to make sure that I'm on the same page. So from the undergraduate abstract algebra, we know the classification theorem, meaning that so for the finitely generated abelian group, so we know it can be classified up to some like the rank with the like the some torsion like the part.
yeah.
So the elliptic curve is just nothing but eventually just the abelian group, as you already pointed out. So as long as we have the isogeny, we already have the abelian group homomorphism from the one abelian group to the other. So from that classification theorem, I assume we already know a lot. So what's the specialty of this like the classes? So why don't one just apply just a general like a theory? So rather than just focusing on the elliptic curves.
You know a lot, but not everything. There's
Can you
small
point out one
amounts that
specific instance? So what's the subtle difference then?
okay. Can you have this to be Z mod 3Z and this to be Z mod 2 cross Z mod 2?
Mm,
The answer is no.
so can you be more precise? So yeah, sorry, I just want to
So
understand more.
can all types of finite groups have an isogeny, basically? Can you give me an elliptic curve with any finite torsion subgroup and another elliptic curve with any finite torsion subgroup and then connect them with an isogeny? The answer is no.
That makes sense. Yeah, yeah. Thank you.
You know a lot, but you
Mm.
don't know everything. So you know a lot, and that's how the research worked. The research was very quick to solve a lot, but it stalled when you were trying to find the very last pieces. And I'll show you a little bit of what I mean. So yes, Gunhee is on the right track. That is how the research works. They're using basic algebraic, using basic group theory and algebra, you can do a lot. But there's still some subtleties. So for example, let's say the Q isogeny class of E is the set of all elliptic curves over E, over the rationals that are isogynous to E by an isogeny that is rational with finite kernel. So if you have such an isogeny class, you can make an isogeny graph with each vertex being an elliptic curve and each edge being an isogeny that maps elliptic curves to each other. And each edge is an isogeny of prime degree, and you can make bigger and bigger isogenies by just gluing different isogenies together. So that's what an isogeny graph is. So you give me vertices that are elliptic curves and edges that are isogenies of prime degree. All right? And so isogeny-torsion graphs are exactly the same thing as an isogeny graph. But now, not only do we just write the vertex as just some basic elliptic curve, we also write the vertex as torsion subgroup. For example, this is the isogeny class 17.8 from the LMFDB. Those of you who don't know what the LMFDB is should go on it now and start clicking on buttons and clicking on things that you can use the LMFDB on, and it'll be very helpful for your research. But they have this classification 17.8. There's an isogeny class they denoted 17.8. It consists of 4 different curves, E1, E2, E3, E4. This is the isogeny graph on the left. You can see that these edges are all labeled with 2, meaning they are isogenies of degree 2. All right, but this is an isogeny graph. We wrote down the degrees of the edges. We didn't really specify anything about the curve. For example, not its algebraic properties or torsion subgroup. This is the isogeny-torsion graph on the right side. Here you see the middle curve, what corresponds to E1, has torsion subgroup Z2 cross Z2. Here, E2 has torsion subgroup Z mod 4Z. Here, E3 has torsion subgroup Z mod 4Z, and here E4 has torsion subgroup Z mod 2Z. So isogeny graph on the left, isogeny torsion graph on the right. So this question is a bit more kind of hashed out with isogeny graphs, isogeny torsion graphs. My question now is going to become not working with just pairs of elliptic curves. Why not work with isogeny graphs, isogeny torsion graphs? Before that, I'm going to talk a little bit about Galois representations before we go into classifications. So let's end our definitions with Galois representations. If E is an elliptic curve, defined Euler rationals, and n is a positive integer, the subgroup of E of elements of order dividing n, so not just order n, order dividing n, 1, maybe 2, n, all of them, again, with coordinates in Q bar, is denoted E bracket n. And we'll call these the n torsion points. So E bracket n is actually also a subgroup of E. We also can classify this as isomorphic to Z mod NZ squared. If you call the absolute Galois group of Q bar as GQ, we have that GQ acts on E and E bracket n for all positive integers n. And given a choice of basis of E bracket n, so E bracket n has 2 generators. It doesn't have just one basis. You can give me any large number of bases. So they're all going to be the same basis up to conjugation. They won't be the exact same, but we can conjugate with each other. We like to study the automorphism group of this. Well, that's kind of like the same thing as studying matrices. If you have these two are designating columns of a matrix, instead of talking about the automorphism group of E bracket n, why not just say the group of 2 by 2 matrices over Z mod NZ? So from there, we have the mod n Galois representation attached to E. So basically, you take this map and you take all the automorphism groups, all the automorphism elements of here, and you tell me how they act on these n torsion points, and that spits out an output here. Basically, you get matrices to tell you how the absolute Galois group behaves on E bracket n. And you have this for all positive n. I like to stop and say, those who want to go into arithmetic geometry, this is the most important topic in arithmetic geometry. This GQ is the most important object in arithmetic geometry. And I think this is the most important topic in arithmetic geometry for me. But GQ is like a central object. You should start getting used to it, start understanding how to work with it. And this map, the mod n Galois representation, is a very nice way to understand properties of elliptic curves, how elliptic curves work, and what the elliptic curves you're working with, how they behave with other objects. Very important. Okay, let's move on. So another important thing between isogenies and subgroups of E. So if you say E is an elliptic curve defined on rationals, and you give me a finite subgroup H of E, then there's an elliptic curve E mod H. So this is not a group. I'm not saying I'm doing a quotient group. I'm not saying that. I'm just saying there's a special group I'm going to denote E mod H. And there's an isogeny phi sub H. Mapping E to E mod H, and phi sub H has kernel H. This is in, I think, towards the end of chapter 3 of Silverman's Arithmetic of Elliptic Curves, a textbook that all arithmetic geometry students should read, at least the first 3 chapters. I would say also chapter 5, I think, and the chapter on the SHA group and later chapters, but at least read the first 3 chapters starting now. And at the end of chapter 3, you will see the proof of all this. This is very interesting. So I didn't say anything about E mod H yet. Both E mod H and phi sub H in isogeny are defined over the rationals, if and only if this absolute Galois group stabilizes the group H. I didn't say every element of H has to be fixed, but I'm saying this H has to be mapped to H. So this group has to be mapped to itself. It doesn't mean every point has to be fixed. The points inside the group can move around, but they have to stay in the group. So if that's the case, we call H to be a Q-rational group. And it's the most important subgroups of my elliptic curves that I worked with. So this is an extremely important property. So if you have an elliptic curve E, there's a one-to-one correspondence between cyclic Q-rational subgroups of E and elliptic curves over Q that are Q isogenies to E up to isomorphism. So if you have a finite subgroup of E that is Q-rational, you automatically get another elliptic curve that is isogenies to E. And because I like to work with group theory so much, this makes life so much easier because it's so much easier to work with subgroups of a group than it is to come up with an elliptic curve out of nowhere that is isogenies to my elliptic curve E. So that's why this theorem is extremely important to me. All right, so let's talk about this one important object before I tell you really what I'm trying to study. So if E is an elliptic curve with an isogeny defined over Q of degree, I don't know, some integer n greater than or equal to 2 with a cyclic kernel, then this topic is going to be very important for your further research. E corresponds to a rational point on the modular curve x naught of n. X naught of n is a modular curve generated by the group of upper triangular matrices over Z mod NC. And this non-cuspidal means it's a nice point. So sometimes you have points that are cusps, and those are points that you have to be careful of. They usually kind of break your theory. So if E corresponds to a rational point on this x naught of n that is not a cusp, then you get an elliptic curve with an isogeny. That's fine, but more importantly, x naught of n has been studied extensively for many years. And we arrived at the conclusion that if you have a positive integer n greater than or equal to 2, for which this x naught of n has a rational point, then n is one of these on these rows, here, here, or here. What I'm trying to say in the first case is that x naught of n is isomorphic to the projective line. That basically means it's a genus 0 curve and it has a rational point. Everything looks very nice. That's great. On the other hand, things get a little bit more interesting when n is any one of these integers. In that case, x naught of n is actually an elliptic curve. But the rank of the elliptic curve, that lowercase r I talked about earlier, is 0. It's an elliptic curve with finely many rational points. On the other hand, if n is one of these 4 numbers, then x naught of n is a curve of genus greater than or equal to 2. Again, there are only finite many rational points in this case, but it's no longer an elliptic curve. All right. That being said, there's a connection between x naught of n
What
and
about the other integers? I'm just wondering, do we know or we just simply do not know?
I don't know the uh, geometric
I
properties of
mean,
x
so
naught.
there should be infinitely many the other like the integers. They might behave
Yep.
something different, right?
So I don't know the geometric properties of x naught of n when n is not one of these integers. But in that case, all the rational points, if there are any, are cusps. And for an arithmetic geometer like myself, I avoid cusps. I only work with rational points. I avoid cusps. And so those are
That makes
points
sense.
those are points I'm scared of. And I don't work with them. Okay, that being said, x naught of n. How is that related to elliptic curves? Well, there's a reformulation of this theorem I told you about, this n being 1 to 10, 12, etc., 25, these numbers here and these numbers here. Well, there's a reformulation of this. Well, what I'm trying to say is let E be an elliptic curve, and for every prime P, let Cp of E be the number of cyclic Q-rational subgroups of E of order of power of P. So order of power of P, no, the number 1 is a power of P, so you're supposed to include that in your number. And this Cp of E is equal to the number of elliptic curves over the rationals that are isogynous to E by an isogeny with cyclic kernel of order of power of P. And C of E, let's say, is the number of Q-rational subgroups of E. That's literally equal to the number of elliptic curves over Q that are isogynous to E. Monsieur Kenku not only classified the rational points on x naught of n, he also reformulated that theorem into this, where for any elliptic curve, Cp of E is bounded below by these numbers here, meaning that each elliptic curve, the number of other elliptic curves that it is isogynous to, by an isogeny of degree, a power of all primes, has these bounds. So for example, any elliptic curve E has at most 8 different elliptic curves that are isogynous to it by isogenies of degree a power of 2, or power of 3, or this power of 5. So for example, let's say you're working with an elliptic curve and C5 of E is equal to 3. So you have an elliptic curve, it's isogynous to itself, 1, and 2 other curves by an isogeny of power of 5. So you could have 1, 5, or 25. So the elliptic curves could be isogynous to elliptic curve of degree 1, of degree 5, or degree 25. Moreover, Kenku saw that C of E is bounded above by 8. All of the curves are isogynous to at most 8 different elliptic curves. And so we can use this to classify all the isogeny graphs. This theorem here. So we can do that now. So isogeny graphs, I said before, was we take a class of isogeny of elliptic curves that are isogynous to each other, and we make a graph out of them. And we label the edges of the graphs with prime numbers, where a prime number is the degree of the isogeny we saw. So with Kenku's theorem, with this classification here, we can actually classify all the isogeny graphs. And we'll go over them now. Note, you can have at most 8 different vertices in an isogeny graph. There are 26 different isogeny graphs. 16 of them are linear, and I denote them as LK. L meaning linear, K being the number of vertices. So what kind of a isogeny graph will be an L1 graph? Well, it's linear, and it has one single elliptic curve. That's it. Is it? E. Just E. What about an L2 graph? Well, it's a linear graph with 2 vertices. Has to be connected by an isogeny of prime degree. What can the prime be? Well, it could be anyone that Cancun theorized. He said 2 through 19, 37, 43, 67, or 163. So this is an L2 graph. What about an L3 graph? Well, you have 3 different curves, each connected by a p isogeny. T could be 3, or it could be 5, and that's it. What if you have an L4 an L4 graph? An L4 graph is a linear graph of 4 different vertices. The only way this happens is if you have a 27 isogeny. 1, 3, 9, 27. So those are all the linear isogeny graphs. Are there any other types of isogeny graphs? Well, yes, there are rectangular isogeny graphs. I call them RK, R being rectangular, K being the number of vertices. There could be only 4 or 6 different types of vertices. So in the case that you have an R4 graph, you have a square-shaped graph. You have this E1, E2, E3, and E4. They're connected by P isogenies here and Q isogenies here. What can P and Q be? Well, the product can be 6, 10, 14, 15, or 21. So 2 and 3, or 2 and 5, or 2 and 7, 3 and 5, or 3 and 7. And there's one type of R6 graph. An R6 graph is a graph where you have a maximal isogeny of degree 3, 9, 18. So an 18 isogeny. We have other types of graphs. These are graphs where you have this curve here, E1, these curves here, E1 and E4, E1, E4, and E6 have flow-through torsion. We'll talk about them later when we're talking about isogeny-torsion graphs, but these are TK graphs, graphs which have flow-through torsion. One of the curves has flow-through torsion with K vertices. You have a T4 graph, so 4 different vertices. You have this E1 has flow-through torsion. We'll talk about that later. We have this T6 graph. So 6 different vertices. These two curves in the middle have flow-through torsion. And you have a T8 graph. These 3 curves here have flow-through torsion. The other curves have cyclic torsion. This curve here has flow-through torsion. The other curves have cyclic torsion. These curves here have flow-through torsion. These other curves have cyclic torsion. These curves here have flow-through torsion. The other curves here have cyclic torsion. There's one final type of isogeny graph. These are S-type isogeny graphs. These are very difficult to work with. These are isogeny graphs with elliptic curves here. E1 and E4 have a 3 isogeny between them, and they both have flow-through torsion. Here, here, here. We call these S graphs because they were very strange graphs, and they also have like an S pattern here. It's a very strange kind of graph. So we classify the isogeny graphs. And my whole point originally was to ask what types of groups we can have, torsion subgroups we can have, between curves that are isogynous to each other. Naturally, the next step is to classify isogeny-torsion graphs, which would answer my question that I originally proposed. So can we classify all isogeny-torsion graphs? Yeah, we just have to take all isogeny graphs and classify the torsion subgroups of their vertices. My advisor Alvaro and I worked on this together. There are 52 of them. 23 of them are LK graphs, linear graphs. 12 of them are RK graphs, rectangular. 13 of them have flow-through torsion. And 4 of them are S-type graphs, flow-through torsion with a 3 isogeny. 16 of those graphs, of the 52, are graphs with complex multiplication, meaning some of the elliptic curves have CM. So for the future reference, this bracket M means a cyclic group of order M, and this bracket 2 comma N means a group of the form 2 Z mod 2 cross Z mod N. N is some integer greater than or equal to 2. So 2, 4, 6, or 8. So now let's quickly go over all the isogeny torsion graphs. Here they are. These are all the linear isogeny torsion graphs. So if you have a graph with a single vertex, you can only have one single torsion subgroup, just the identity. Or if you have a graph with two vertices, you can have this is a Z mod MZ, but this has to be trivial. If P is any prime isogeny greater than or equal to 11, this Z mod MZ also is trivial. But when P is 3, 5, or 7, M you can have to be Z mod PZ, or it could be trivial. So if you have this to be a 3 isogeny, you could have this to be Z mod 3Z, or you could be trivial, and that's it. Here, if you have a 2 isogeny, both the torsion subgroups are the same. Here you have, if you have a 9 isogeny, you could have a Z mod 9Z. You could. Or if you have a 3 isogeny here, you could be Z mod 3, Z mod 3, 1. Or if you have a 5 isogeny, you could have Z mod 5, Z mod 5, 1. Or of course, you could have 1, 1, 1, the most natural idea. In the case that you have a 27 isogeny, all these Z mod MCs are the same. They could all be trivial, or they could all be Z mod 3Z. Moving on, these are examples of all the isogeny-torsion graphs that are linear. So without examples, how do you know that they actually exist? You need to find examples. I got all these examples from the LMFDB. If we move on to rectangular graphs, here you have an isogeny of even degree, 2p. You could have this to be p equals 3, so 6 isogeny, 2 times 3, or you can have p as 5, so 2 times 5 is 10, or you can have p as 7, 14. In the case that you have 3 or 5, Z mod m could be Z mod 6, or it could be Z mod 10. Or all of them could be Z mod 2. Don't know. Any one works. In the case that you have a 15 isogeny like this, you could have everything as trivial. Or you could have both of these are Z mod 5, and this is both trivial. In the case that you have a 15 isogeny this way, you could have everything as trivial. Or you can have both of these here are Z mod 3Z. In the case of 18 isogenies, you could have everything as Z mod 2. Or you could have these four curves have Z mod 6Z torsion. But these on the very right side and these on the very right side always have to be Z mod 2. The only variation happens with these four. These are all the examples of rectangular isogeny-torsion graphs. And this classification is from the notation of the LMFDB. Moving on.
Yeah, sorry, Garen. I feel this is almost like a crazy, So, why don't we just stop to like the present further of the slide? I know even those are the rest of the slides are for the classification result, but I wanna actually more appreciate it if you don't mind. So, what about we just make the discussion up to like this point, and we can just continue next time if participants or any of you request to just finish our slides today. I don't think
Okay.
really.
Okay. Yes. So let's stop at the rectangular isogeny-torsion graphs. There are more. I'll show you quickly, but I'll go over it later. So these are the last, like another 7 or so. But let's stop at the rectangular isogeny-torsion graphs. So I haven't shown you how Galois representations affect isogeny-torsion graphs, but I almost finished the classification of isogeny-torsion graphs. I think that's an important place to stop. So we will continue with the full classification of isogeny-torsion graphs later, and then see how Galois representations can be used to work with isogeny-torsion graphs. Okay.
I have some quick questions about this graphings and stuff. So if actually we can have a look at this example. For example, if I have an edge from E1 and E2, and you usually put the single prime number there. First question is, does an edge count the multiplicity? Can we have multiple isogenous with the same order from E1 to E2 with the same and like can we have the case where E1 to E2 isogenous but with different prime numbers?
No.
think
My
there should be
classification
some.
my classification of isogeny torsion graphs are complete. That's my answer to you. Your question is missing a property. You want to say cyclic. Can we
Mm-hmm.
have can we have different isogenies between elliptic curves that are so can we have rational elliptic curves that are connected by isogenies that are rational? Yes, we can. But when you start talking about cyclic isogenies, like I'm working with, things get very rigid. Take the example of this isogeny I gave you. You can have infinitely many isogenies between these two elliptic curves. But how many can you have of degree 2 that are rational? How many? One. This is it. The others you could have when they are not cyclic. For example, you could have this 2 isogeny that I drew for you. There's nothing wrong with that. But you can also have an 8 isogeny. What's the difference between 2 and 8? Well, you scale by a multiple of 4. 4 is a square number. So how would you get a scaling of 4? Why not? The multiplication by 2 map. So if you want, let's say, an isogeny of degree, um, let's say 50, how do you do it? Well, you can have my 2 isogeny I gave you here, but you're now missing a factor of 25. 25 is a square number. Why not do this isogeny of degree 2 followed by a multiplication by 5 map? That gives you an isogeny of degree 50. But is that cyclic? No. So the question that you asked is yes, what you asked is open ended. So you could have many isogenies between elliptic curves, but I restrict you severely when you say those isogenies have to be with a cyclic kernel. How do I restrict you? By that here. Where am I saying? There's a one-to-one correspondence between cyclic rational subgroups of E and their corresponding isogenous elliptic curves. So two elliptic curves can have an isogeny between each other, fine. If the isogeny is cyclic, then that's the only isogeny you can have with a cyclic kernel. You can have other isogenies once you introduce multiplication by m, other things I don't know, but with a cyclic kernel, no. The answer to your question is no.
Yep. Thank you very much.
So for that matter, an elliptic curve to itself has infinitely many maps. Of course, the multiplication by m maps. But how many cyclic isogenies? I think the only one is a trivial map, the identity map.
Kennedy?
Yeah, the identity map. Um, I'll think about your question some more just to make sure I didn't make a mistake. But this is why I worked with cyclic isogenies, because otherwise these graphs could have very many vertices, very many loops, very many differences. The only reason why I'm certain there's only one line between two of these elliptic curves is because the isogeny is prime. It is cyclic. So I'll think again about that question just to make sure I didn't make a mistake. But that's a good question. But the reason why everything works is because kernels are cyclic for me.
I basically have two different types of the comment regarding your talk today. Yeah, I really like the appreciate these types of the classification. Yeah, classification. Yeah, I really basically love it. And so in terms of this like the new concept of the isogeny graphs. Yeah, yeah. So yeah, classify all those possible like the cases. Yeah, yeah, that would be great. But at the same time, this is not pointing out the drawback, but I just want to share the perspective from topology and geometry in the sense that this seems already too narrow down just by just looking at just focusing on the elliptic curve structure in my perspective. So for example, it seems so this like the basic setup. The graph is just an eye graph consists of the vertices and edges. But from algebraic topology point of view, for example, so the graph should be regarded as a functor. So it's a pre like a simplicial presheap. And if one just regard the graph as a so for example, the abelian group can be realized as a abelian groupoid. So the elliptic curve can be realized as a groupoid, and the group homomorphism can be realized as a sort of a functor. The one of the benefit for regarding that manner is that there's a higher homotopical information that described in terms of group like the cohomology. So even this is a very like nice way to classify the orthostatic elliptic curve in terms of the torsion group. I completely agree with it, but at the same time, one of the like the direction to head out is to just look at some algebraic topological like a perspective to just view this like the graph in a with the higher like the homotopical data. Then one can actually try to dig something further. So I can give some like the introductory level of the like the concept of groupoid and how we regard the group homomorphism as like a functor in a very elementary way, so that everyone can just feel this is very accessible. So that Garen might just gradually jump into these types of the research further. That's one thing. But at the same time, so this is my second feedback. Actually, I want to make the conversation, I mean, the discussion in this seminar more like the accessible way. In order to do it, I also want to get some like the presentation from John as well, so that we can really like the see we are all on the same page of the what was really going on before and what types of problems we can attack together. And if there are some like the questions, and even the participant can also try to think about it together. So I definitely agree that Garen has a rest of the slides to finish for next time. But if you don't mind, what about just John give some presentation about like his like the research like the direction, at least very naively. And meanwhile, so if there are no like the speaker, I can talk about some like the algebraic topological perspective regarding this like the concept of isogeny graph with a very concrete like the example, so that we can just look at it together. So that's my suggestion. And rest of the slide we can maybe discuss further once we have a more clear understanding regarding the isogeny graph. So how about it? So John
Yeah,
might
no problem.
do yeah
No problem.
something next time. So
Yeah, yeah,
so
yeah,
so
no problem.
yeah, John, what do you think? This
Yeah,
might.
I'm all good. Actually, I have a like conference to attend next month at like 4 weeks from today. So if I can just like jump on like 2 weeks from today and give a talk, then move over to Garen again, then I would really appreciate it, of course.
Yeah. So if we have like the like the complete of the schedule, then we might just skip some of the like the even the
Yeah,
month.
it can happen.
Yeah,
Mhm.
yeah, absolutely. Yeah. All right. So is there any other like the questions or comments regarding today's like the presentation?
I'd like to mention one thing. The first objective of this talk is to classify all the pair of torsion subgroups, right?
It was,
And you are
yes,
all yes, and you are considering torsion isogeny graphs and isogeny torsion graphs, and
yes,
you are the edges are of prime order. Why are
yes.
you only considering prime orders?
Prime order, because all isogeny graphs that are cyclic, the degree is multiplication of prime. So the other isogenies of cyclic, the other cyclic isogenies degrees you can get from multiplying these prime numbers. There are no others.
When you're considering only cyclic subgroups?
Yes.
And then why are you only considering cyclic subgroups?
The other ones are just multiplication by M maps. So you have a cyclic isogeny, and then you can compose by multiplication by M. Multiplication by M is nice, but I don't care. It's just the same elliptic curve. I don't care. Let me
Essentially,
go.
you're extracting crucial informations.
Yes. The only
Not only excluding redundant ones, right?
yes. The only isogenies that are of cyclic kernel can be of these degrees, 1 to 10 to 25, 11 to 27, and these four. So I don't care about anything else. Even if you have an isogeny of degree 100, that's very nice. It could work. That's multiplication by 10, or it could be multiplication by 5 and then a 4 isogeny somehow. But really, when you're working with cyclic, you only care about these degrees here. So there's about, I don't know, 40? I'm not sure.
And then what is the essential tool for proving these classification theorem?
Do you mean this exact one or the one I was
No,
doing?
not just classification of the isogeny graph.
It's a great question. What I did is I tried to see which one of these numbers can fit into a graph. So if I do, let's say 21, 21 is 3 times 7. So that automatically gives you a rectangular graph. And then I used Kanku's actual paper, and he said after 21, you can't have anything else. So he specified a little bit more in detail. After you have like 3, C3 of E is 2, and C7 of E is 2, he wrote in his paper, that's enough. So he gave more detailed bounds of not just these numbers by itself, but products of these numbers. So once you see that you can't have more isogenies after 21, you just draw this rectangle and you're finished. So Kanku gave individual bounds for these. He also gave bounds for the products. I wasn't writing everything in detail, but this is usually how he is cited. But you're right, I should have written more. He writes everything, basically wrote everything. The one thing that he didn't write that you have to do by yourself, I didn't really say much about this yet, but here is a 4 isogeny from E3 to E4. 2 times 2 is 4. When you go through a 4 isogeny, the curve in the middle has full 2 torsion. Kanku, I don't think, saw that when he was writing his paper. This is purely an elliptic curves property. So if you look at here again, if you look at any 4 isogeny, 2, 2, this curve in the middle has full 2 torsion. 2, 2, full 2 torsion. Or 2, 2 here, full 2 torsion. That is the only thing that I came up with that was not in Kanku's paper. So these isogeny graphs really are equivalent to Kanku's paper.
Okay,
So
thank you.
to answer your question, how I classified isogeny graphs was really I just do a little bit more group theory and I arrived at my answer.
Yeah, so I naively imagine that if this like the isogeny graph is regarded as now the simply pre-shape, then the highlight of homotopy data could be realized as a Galois cohomology. So yeah, there should be something further to make some progress. So I'll try to be accessible. So that if I have time to present. But for next like so after 2 weeks, John will just prepare what he have done so far and interest like the topics that he'd like to share in this seminar. And yeah, so let's try to just make some like a presentation in turn in a way that we can just make the same page of the each of the non-trivial like the topics and concepts, and we can discuss anything further. So maybe we can just stop to like the record the very first like a seminar. It was fantastic. Thank you very much for the wonderful talk.